So earlier I went through a homework and we talked about how to evaluate vectors and kind of how to use them, finding length and derivatives and things like that, just a little bit, and doing dot products, but mostly that involved kind of the algebra of using vectors. Well, today we're going to actually kind of dive into the calculus of using vectors and parametric equations. And because parametric equations and vectors tie in really closely to one another, I'm going to do this together. So I'm just going to work through our homework together here. It will probably take a little while. There's quite a few problems, but I think the more problems we do, the better we will understand this and be able to really kind of complete this well. So let's just begin here. If x equals t squared minus 1 and y equals e to the t cubed, 2t cubed, find dy over dx. Well, we know that dy over dx is the same as dy over dt over dx over dt, right? So the derivative of x with respect to t is going to be 2t. Oops, let's start with our y. Or the derivative of y, so the derivative of t cubed is going to be 3t squared, of e to the t cubed, over the derivative of our x is just going to be 2t. And that's actually our answer for number 1. Okay, so that was simple enough. Number 2, if a particle moves in the xy plane so that any time t is greater than 0, its position vector is the natural log of t squared plus 5t and 3t squared, find its velocity vector at time t equals 2. Well, we know that our velocity is going to be the derivative of these. So our velocity vector is going to be, the derivative of this is going to be, it looks like 2t plus 5 over t squared plus 5t. And the derivative of our y component here is just going to be 6t. So now we're asked to find this at 2. So our velocity at 2 is going to be equal to 2 times 2 plus 5 over 2 squared plus 5 times 2, and then 6 times 2, which is going to be 4 plus 5 is 9 over 4 plus 10 is 14, and 12. These first ones are pretty easy, I think. A particle moves in the xy plane so that any time t, its coordinates are given by x equals t to the 5th minus 1, y equals 3t to the 4th minus 2t cubed. Find its acceleration vector at t equals 1. Well, I'm going to do these separately. So x prime is going to be equal to 5t to the 4th, and x double prime is going to be equal to 20t cubed. Whereas y prime is going to be equal to 12t cubed minus 6t squared. And y double prime is going to be equal to 36t squared minus 12t. So our acceleration vector at t is going to be equal to 20t cubed, comma, 36t squared minus 12t. And we were asked to find that at 1. So a of 1 is going to be equal to 20, comma, 36 minus 12 is 24. If a particle moves in the xy plane so that at time t, its position vector is sine of 3t minus pi, 3t squared, find the velocity vector at time t, pi over 2. This is pretty similar. So our velocity of t is going to be equal to 3, because that's the derivative of what's inside, times the cosine of 3t minus pi over 2, and then 6t. And if we find v at pi over 2, we get 3 cosine of 3 pi over 2 minus pi over 2, then 6 times pi over 2. So this is just going to become pi, right? Cosine of pi is -1. 3 times -1 is -3. And this is going to simplify down to 3 pi. A particle moves in the curve y equals ln of x, so that its x component has a velocity x prime t equals t plus 1 for t greater than or equal to 0. At time t equals 0, the particle is at the point 1, 0. We want to find the position of the particle at t equals 1. Well, first we need to find the position. So x of t is going to be equal to the integral of t plus 1 dt. So that's going to be equal to 1/2 t squared plus t plus c sub 1. I'm going to use a sub 1 because I might have to find another one later. But you could just use c as long as you keep it straight. Well, we know that at time t equals 0, the particle is at the point 1, 0. So x of 0 is equal to 1/2 times 0 plus c sub 1, which equals 1. Therefore, c sub 1 is equal to 1. So x of t is going to be equal to 1/2 t squared plus t plus 1, right? Well, y is equal to the ln of x. So y of t is going to be equal to the natural log of 1/2 t squared plus t plus 1, right? So now we can actually write our vector, our position vector, at 1. So our position vector, I'm going to call that s, is equal to 1/2 t squared plus t plus 1, ln of 1/2 t squared plus t plus 1. And s at 1, I should probably put that there, it's going to be equal to 1/2 plus 1 plus 1, ln of 1/2 plus 1 plus 1, which equals 5/2 natural log of 5/2. Okay. A particle moves in the xy plane in such a way that its velocity vector is 1 plus t cubed. If the position vector at t equals 0 is 5, 0, find the position of the particle at t equals 2. Well, I think this is going to be pretty similar to what we just did. So we need to find, this is our velocity vector, so this is x prime and y prime. So x of t is going to be equal to the integral of 1 plus t dt. So that's equal to t plus 1/2 t squared plus t sub 1. Likewise, y of t is equal to the integral of t cubed dt, which equals 1/4 t to the 4th plus c sub 2. This is a good example of why I'm using c sub 1 and c sub 2. So I know that x of 0 is going to be equal to 5, right? So I have 0 plus 1/2 times 0 squared plus c sub 1 equals 5. So c sub 1 equals 5. And then here I know that y of 0 is going to be 1/4 times 0 plus c sub 2 equals 0. So c sub 2 equals 0. So now my position vector s of t is equal to t plus 1/2 t squared plus 5, and then 1/4 t to the 4th. And we were asked to find it at 2. So s of 2 is equal to, looks like it's going to be 2 plus 5 is 9. And then 2, this is going to be 4. Right? So a particle moves along the curve xy equals 10. If x equals 2 and dy over dt equals 3, what is the value of dx over dt? Well, we know that y is equal to 10 over x, right? So that's equal to 10x to the negative 1. So dy over dx is going to be equal to negative 10 over x squared, right? Well, we also know that dy over dx, or dy over dt is equal to 3. So dy over dx is going to be equal to negative 10 over x squared, which is equal to 3 over that dx over dt. And that's what we're trying to find, right? So we can do a little bit of multiplication here. We're going to end up getting 3x squared is equal to negative 10 dx over dt. So dx over dt is going to be equal to 3x squared over negative 10. And we're actually asked to find this if x equals 2. What's our value? So dx over dt evaluated at x equals 2 is going to be 12 over negative 10, which equals a negative 6/5. Okay, number 8. The position of a particle moving in the xy plane is given by the parametric equations x equals t cubed minus 3/2 t squared minus 18t plus 5, and y equals t cubed minus 6t squared plus 9t plus 4. For what values is the particle at rest? Well, it's going to be at rest when x prime of t is equal to y prime of t. Right? So when's that going to happen? Well, first I need to find my x prime is going to be 3t squared minus 3t minus 18. And my y prime is going to be 3t squared minus 12t plus 9. And I can actually solve here. So I'm going to have, is that right? Nope, minus 6. What am I thinking here? Minus 6. So here I'm going to get t equals 3 and t equals negative 2. For y prime, if I solve, I'm going to get t equals 3 and t equals 1. So when are y prime and x prime equal? Well, when t equals 3. So it's at rest at time t equals 3. Good. A curve C is defined by the parametric equations x equals t cubed and y equals t squared minus 5t plus 2. Write an equation of the line tangent to the graph of C at the point 8, negative 4. Okay, well, we can do this writing a line tangent. We've done that a number of times. But the first thing that we're going to need to do is to actually find our derivative, right? Well, dy over dx is going to be equal to, our derivative of y is 2t minus 5. And our derivative of x is 3t squared, right? And now we need to find out what actually is our value of t, right? So when x is equal to t cubed, it's equal to 8. Well, the cubed root of 8, t is going to be equal to 2, right? So if we evaluate this at t equals 2, we end up getting 4 minus 5 is negative 1 over 12. That's our slope, right? So now I can actually write this equation of the line. So y plus 4 is equal to negative 1/12 times x minus 8. Good? All right, now we're actually going to be able to use a calculator, which I think is important because as we go on, these questions can get more complicated, and I think they're more likely to be on the AP exam. So using a calculator and knowing how to use them will be helpful. All right. So a particle moves in the xy plane, so the position of the particle is given by x of t equals 5t plus 3t, so 3 sine of t, and y of t equals 8 minus t times 1 minus cosine of t. Find the velocity vector at the time when the particle's horizontal position is x equals 25. Okay, well, first thing that we're going to need to do is actually find out what time the horizontal position is at x equals 25. So I'm going to set 5t plus 3 sine t equal to 25. Therefore, 5t plus 3 sine t minus 25 is equal to 0. So now this is where our calculator comes in. Okay. So I'm going to go, I'll quit this, but if you go to math and then go down to like up one, but it'll go to B, solver, okay? And you'll be able to type in here, you'll have this equation, and we can type in what we have here. So 5t plus 3 sine of t minus 25. And then we're going to hit enter. Well, this isn't done yet. We need to actually put in what we think t is going to be, okay? And I'm going to put in 5. I'm going to estimate that t is about 5. Then I'm going to hit second and solve down here, okay? So second, solve, and I actually get, oh, what's that? Second solve. What the heck? Hold on. Sorry, I know what I was doing. I was pushing second solve, but what I need to do is push alpha solve. So you have this, and then hit enter. And then I need to push alpha, solve. So alpha, I'm going to put in 5, alpha, solve, and I get this number. So t is 5.445755, okay? So t is equal to 5.447755. And I actually want to go back to my calculator, quit here. So 5.44575, and I want to store that. So I'm going to go down here to STO, that's going to store, and then I'm going to say alpha A, so that I have that stored there, and I'm going to use that number further. So I'm going to store this as alpha A, and now I want to find the velocity vector. Well, the velocity vector is going to be at t, or sorry, not at t, but at a. The velocity vector is going to be at time, this time a, right? So velocity vector at a is going to be equal to, I'm going to have x prime of a, comma, y prime of a. Well, that isn't really done yet, is it? So now we need to go back to our calculator and actually calculate this. So I'm going to type in math 9, or not math 9, clear. I'm going to type math 8. And I need, before I even do this, I need to go up to my y equals. So go to y equals, and I need to make sure that my x and my y are the same, okay? So as what's on my paper here. So I'm going to type in 5t plus 3 sine of t, and 8 minus t times 1 minus cosine t. Okay. So I don't need to graph these, but then I again go back here. I'm going to do math 8. So this I can calculate the derivative with respect to t of, well, what am I going to find the derivative of? I need to type alpha and then here trace, alpha trace, and I can find my derivative of x of 1. We already put that function in, evaluated at alpha a, right? That's what I'm trying to do. And if I enter this, I get a number. So I get 7.008. There's my first value. And then I can do the same thing. I'm actually going to just copy it and change this here. Instead of having x of 1, I'm going to do, instead of having x sub 1, I'm going to do y sub 1, t. Again, evaluated at a, and I get negative 2.228. So there it is. There's actually my velocity vector at that time, alpha a. Good? Okay. Some free response questions. We are given the position of a particle at any time t is greater than or equal to 0 is given by x of t equals t squared minus 3 and y of t equals 2/3 t cubed. We want to find the magnitude of the velocity vector at time t equals 5. Well, first I need to find x prime of t is equal to 2t. Y prime of t is equal to 2t squared. So v of t is equal to 2t comma 2t squared, and v of 5 is equal to 10 comma 50. All right, so now I can actually find the magnitude of v. That's going to be the square root of 10 squared plus 50 squared, which equals the square root of 100 plus 2500, which of course just equals the square root of 2600. And I'm just going to leave it like that. I don't really feel like simplifying. What if I want to find the total distance of the particle from 0 to 5? Well, total distance is going to be an arc length, right? From 0 to 5 of the square root of, and we're going to use our derivatives here. Square root of 2t squared plus 2t squared squared dt. Okay. I guess I'll just keep going. So that's going to be 0 to 5. I would speed up through this part if I were you. 4t squared plus 4t to the 4th dt, which of course is 0 to 5 of 4t squared times 1 plus t squared dt. which is 0 to 5 of 2t, 1 plus t squared, dt, u equals 1 plus t squared, du equals 2t dt. Those 2's are going to cancel out, t's are going to cancel out, so we're going to get the square root of 0 to 5 of u to the 1/2 du, which equals 2/3 times 1 plus t squared to the 3/2 from 0 to 5, which 2/3 times 26 minus 1, 26 to the 3/2 minus 1 to the 3/2, which is about 5.1842. Okay. Now, finally, we need to find dy dx as a function of x. Well, x is equal to t squared minus 3, and y is equal to 2/3 t cubed. So I'm going to put x in terms of t. So t squared is equal to x plus 3. T is equal to the square root of x plus 3. This has to be positive because t can't really be negative, right? So y is going to be equal to 2/3 times the square root of x plus 3 cubed, which equals 2/3 times x plus 3 to the 3/2. So dy over dx, we're going to find that derivative. We're going to end up just getting the square root of x plus 3. All right, so far so good? Hopefully yes. Let's do another free response question here. Okay, point xy moves in the xy plane in such a way that, this should be separate, that dx over dt equals 1 over t plus 1 and dy over dt equals 2t. Find the coordinates of p in terms of t when t equals 1, x equals ln of 2, and y equals 0. Okay, well we know our x prime and our y prime, so we need to actually find our x and y. So x of t is equal to the integral of 1 over t plus 1 dt, which of course is the natural log of t plus 1. And I want you to remember here, we're going to have that plus c sub 1. Okay? And then y of t is equal to the integral of 2t dt, which is just going to be t squared plus c sub 2. So now x of 1 is equal to the ln of 1 plus 1 plus c sub 1, which equals ln of 2. So c sub 1 equals 0. And y of 1 is equal to 1 plus c sub 2, which equals 0. So c sub 2 is equal to negative 1. So now we can find the coordinates of our point P. So P of xy is equal to the ln of t plus 1, comma, t squared minus 1. All right. Now we're asked to write an expression expressing y in terms of x. Well, x is equal to the natural log of t plus 1. We're going to solve this for t. So y is equal to t squared minus 1, right? We want to have y in terms of just x only. So e to the x is equal to t plus 1. So e to the x minus 1 is equal to t. So y is equal to e to the x minus 1 squared minus 1. And I would just leave that like that. I would not do any more than that. Not worth it. All right, now we're asked to find the average rate of change of y with respect to x as t varies from 0 to 4. Well, our average rate of change, if you remember from units past, is going to be y of 4 minus y of 0 over basically that x of 4, x of 0, right? So y of 4 is going to be, and see here that this is as t varies from 0 to 4. So this needs to be really not 4 minus 0, but really like our x of 4 minus our x of 0, right? Okay, so y of 4 is going to be, and we have that up here, going to be 16 minus 1 minus 0 minus 1 over, and our x of 4 is going to be the natural log of 4 plus 1 is 5 minus the natural log of 0 minus 1 is oh, 0 plus 1. There we go. Sorry. 0 plus 1 is just 1. Well, what's this equal? So this is 15 plus 1, right? So 15 plus 1 is 16 over natural log of 1 is 0, the natural log of 5. Okay? We're also asked to find the instantaneous rate of change of y with respect to x when t equals 1. Well, our instantaneous rate of change is just our derivative, right? So dy over dx. We were actually already given, or we're not given this, but we can find it. Dy over dx is going to be 2t over 1 over t plus 1, which is the same as 2t times t plus 1, which is equal to 2t times t plus 1, right? And dy over dx evaluated at t equals 1 is just going to give us 2 times 1 times 1 plus 1, which equals 2 times 2 is 4. Okay? All right. Only 2 more pages here, and then I'll be done with this super long video, but that hopefully was helpful at least. 1 more free response, and then we'll do a few multiple choice here. Consider the curve C given by the parametric equations x equals 2 minus 3 cosine t and y equals 3 plus 2 sine t for negative pi over 2 to pi over 2. We want to find dy over dx as a function of t. Well, x of t is equal to 2 minus 3 cosine t. X prime of t is equal to 3 sine of t. Y of t is equal to 3 plus 2 sine of t. So y prime of t is equal to 2 cosine of t. So dy over dx is just going to be equal to 2 cosine of t over 3 sine of t. Or if you want, you can write this as 2/3 cotangent of t, but you don't really need to. Now we're asked to find an equation of the tangent line at the point where t is equal to pi over 4. Well, we need to first evaluate this. Let's first get our point. So x of pi over 4 is equal to 2 minus 3 cosine of pi over 4. That's going to equal 2 plus 3 radical 2 over 2. Y of pi over 4 is equal to 3 plus 2 sine of pi over 4, which equals 3 plus radical 2. Okay, so now we've got our x and our y points, and our dy over dx evaluated at t equals pi over 4. You're going to get 2 cosine of pi over 4 over 3 sine of pi over 4. And that ends up equaling 2/3. So now we can actually write our equation. So y minus 3 plus radical 2 is equal to 2/3 times x minus 2 plus 3 radical 2 over 2. And that's good enough. Okay. We have our calculators permitted here again. The curve C intersects the y-axis twice. Approximate the length of the curve between the two y-intercepts. Well, when is it intersecting the y-axis? Well, that's happening when x of t is equal to 0. So 2 minus 3 cosine of t is equal to 0. So we can solve that cosine of t is equal to 2/3. That's a 2. So t is approximately plus or minus 0.84106. So what's this length going to be then? Well, our length is going to be from negative 0.84106 to positive 0.84106 of the square root of 3 sine t squared plus 2 cosine t squared dt, which is approximately 3.7565. Okay. All right, let's just do a few multiple choice. And just wrap this up, I guess. Okay, a parametric curve is defined by x equals sine of t and y equals cosecant of t for 0 is less than t is less than pi over 2. We want to know what this curve is doing. So it looks like if we want to know if it's decreasing or increasing, concave up, concave down, we're going to have to do a first derivative test. Okay, so first we need to find our derivative here, right? So dy over dx is going to be equal, well, our derivative of cosecant is negative cosecant t cotangent of t. Don't forget that that t there. Please don't don't forget this t right here. Over, derivative of sine is cosine of t. If I rewrite this out, I get negative 1 over sine t times cosine t over sine t times 1 over cosine t. So this is going to be negative 1 over sine squared t, okay, which is equal to negative sine of squared of t, right? To the negative 2, I guess. So what's happening here? Is this increasing or decreasing? Well, this is going to be less than 0, so this is decreasing. So now actually we can cross out a and b, right? Then we can find our second derivative. So d squared y over dx squared is equal to, now, the biggest thing that people forget is how to do these derivatives for parametric. So don't forget the second derivative is d over dt of negative 1 over sine squared t over the original dx, which in this case is cosine of t. So this is going to be equal to, once I simplify it all, 2 over sine cubed of t. Well, that's going to be concave up. So our answer is actually C, okay? Concave up from 0 to pi over 2. That's where I'm evaluating this. Okay. The parametric curve defined by x equals ln of t, y equals t for t greater than 0 is identical to the graph of which function? Well, looks like here I have all of these y's in terms of x, so all I have to do here is eliminate the parameter. So if x equals the natural log of t and y equals t, I need to write x in terms of t. So e to the x is equal to t, so y is equal to e to the x. So looks like, oh, I've got 2 of these, so it's not here, not here, not here. Y equals e to the x when? Well, for this, it's when t is greater than 0. So x is equal to ln of, well, anyway, y, when y is greater than 0. So our answer is actually going to be not for all reals, but for x greater than, oh, no, shit. Sorry, students. This actually is for all reals, sorry. For when y is greater than 0. So this is for when y is greater than 0, so when x is all reals, okay? All right, last one. The position of a particle in the xy plane is given by x equals t squared plus 1 and y equals the natural log of 2t plus 3 for all t greater than or equal to 0. The acceleration vector of the particle is what? Well, our position vector is t squared plus 1 natural log of 2t plus 3. Our velocity vector is going to be 2t, then 2 over 2t plus 3. Our acceleration vector is going to be 2, comma, looks like it's going to be negative 4 over 2t plus 3 squared. Do we have one of those? It looks like it is E. Okay. I know that was a long video and kind of a lot to take in, but I think it's a good way to get more practice with particle motion and acceleration, velocity, and everything dealing with parametrics and vectors. So I'll see you later. Bye.